instructions that execute very quickly, often in a single clock cycle. Interestingly, the x86 processors remains one of the very few mainstream architectures that still use a CISC instruction set today. Excuse me. Intel also tackled another major performance issue, which is the memory access speed. Accessing memory is much slower than executing instructions inside the CPU. To address this, the 8086 introduced architectural techniques that reduce the performance penalty of memory access. Additionally, the 8086 could be paired with 8087 floating point coprocessor. This was a separate chip dedicated to excuse me, handling mathematical calculations involving decimals. This significantly boosted performance for scientific engineering and graphical application. The success of the 8086 didn't happen in isolation. It became deeply connected to another major event in computing history, which is the rise of IBM PC. In the late 1970s, the personal computer market was dominated by companies like Commodore, Atari, Apple, and Tandy. This market was growing rapidly, over 40% per year in the early 1980s. This explosive growth caught the attention of the IBM, a company traditionally focused on mainframes and enterprise systems. IBM decided to enter the personal computer market, and for its CPU, it chose Intel's 8086 architecture. For its operating system, it partnered with a young company called Microsoft. This decision shaped the future of computing. Excuse me. The IBM PC became the standard for personal computers. Microsoft's operating system became the dominant software platform, and the Intel's 886 or the x86 architecture became the foundation of modern computers, legacy that continues to this day. Together, Intel, IBM, and Microsoft formed a powerful trifecta that defined the direction of computing industry for decades. Now, the early days of computing, let's talk about the excuse me. Now, in the early days of computing, the machines were massive, expensive, and incredibly limited by today's standards. During the 1960s, most computers were mainframes, huge systems shared by many users at the time. Efficiency was everything. Every second of CPU time mattered. This need for efficiency gave rise to a concept that would later define modern computing: multitasking. Originally, multitasking didn't exist in the way we understand it today. Instead, early systems used a crude method known as multi-programming. In this setup, multiple programs were loaded into memory at once. The CPU would jump between them whenever one of the programs had to wait for something like input from a keyboard or data from a disk. Rather than letting the CPU sit idle, the system would switch to another program that was ready to run. This simple idea dramatically improved performance and resource usage. Over time, this approach evolved into what we now call time sharing, where multiple users could interact with the same system simultaneously. Now, the problem with single process systems. Excuse me. In traditional single process environments, running a program had full control of the CPU and system resources that might sound efficient, but it created major problems. Excuse me. If a program crashed, the entire system could go down with it. If it entered an infinite loop, everything else would freeze. And from a security perspective, any program or application uh, that would potentially access or overwrite sensitive memory as software could grow more complex. These limitations became unacceptable. Multitasking introduced a new approach. Instead of one program owning the CPU, the operating system rapidly switches between multiple processes, giving each one excuse me, a small slice of time to run. This creates the illusion that everything is running at once, even though one process is executing at any given moment. Early multitasking systems relied on something called cooperative multitasking. In this model, when a process was given the CPU time, it was expected to voluntarily return control back to the operating system. This sounds polite, but it was dangerously fragile. If a program misbehaved or simply forgot to give up control, it would freeze the entire system. One faulty program could bring everything down. To solve this, the engineers developed preemptive multitasking. With preemptive multitasking, the operating system, not the program, controls when a process runs and for how long. Each program gets a small time slice. When it expires, the OS forcibly switches to another process. This made systems far more stable, responsive, and reliable. Three qualities the modern users now take for granted. Multitasking also created another major problem, so we have never endless problems. Now, this problem is memory safety. If multiple programs were running at once, how could the system prevent one program from accessing another or corrupting another program's memory? The solution was a dedicated hardware component called the MMU, or the Memory Management Unit. Excuse me. The MMU sits between the CPU and the RAM. Every time a program tries to access memory, the MMU checks whether that access is allowed. If a program attempts to read or write to a memory region it doesn't own, the MMU triggers a hardware fault. This fault forces the excuse me, operating system to step in, protecting the system from crashes and security violations. Some MMUs also introduce the idea of privilege levels. Memory regions could be marked with different levels of trust. Lower privilege code, like user applications, could not access high privilege memory used by the kernel or operating system. This created a strong security boundary between user programs and critical system components. Excuse me. Another revolutionary idea that came from this era was the virtual memory, or VRAM. It's an abstraction over a physical RAM. Instead of programs directly accessing physical memory, they operate in a virtual address space. Behind the scenes, the MMU maps these virtual addresses to real physical memory locations, allowing systems to run programs larger than available RAM, isolated processes from each other, move memory around dynamically, swap unused memory to disk. Today, virtual memory is a core feature of all modern operating systems. Now, in January 1983, the Apple released the Lisa, followed 1 year later by the Macintosh. These machines were revolutionary not just for their graphical or user interface, but also for their underlying hardware. The Macintosh ran on the Motorola 68K processor. What made the 68K was special was its early adoption of the 32-bit internal architecture. However, it wasn't a true 32-bit processor in every sense. It was more of a hybrid between 16-bit and 32-bit. Despite this, it was extremely capable. More importantly, the 68K supported a basic form of privilege separation. It could operate in one of two modes, user mode and supervisor mode. Now, let's move on. By the end of the 1984, IBM released the PC-80. This is the second generation of a personal computer. Alongside it, Microsoft continued developing Windows, a project that had started back in 1981. Windows 1.0 officially excuse me, debuted in November 1983. At the heart of the IBM PC-80 was the Intel 8020-286 processor. The CPU was groundbreaking. It was the first mass-produced processor directly support multi-user system with multitasking built into the hardware. Several major architectural improvements made this possible. First, the 8286 eliminated multiplexing on the data and address buses. This simplified communication between components and improved performance. Second, it moved memory addressing control into a dedicated block of hardware, effectively integrating an MMU-like system directly into the CPU. And third, it featured an improvement in instruction prefetch unit, known as the instruction unit. It could decode up to 3 instructions from 8 bytes prefetch queue, boosting efficiency. Excuse me. Now, the 8286, it can address up to 16 megabytes of RAM using 24-bit addressing. This made the old 8086 memory model insufficient. To solve this, the Intel introduced the protected mode. Protected mode allowed the CPU to enforce memory protection, support multitasking, use virtual memory, isolate processes, implement privilege levels. In protected mode, memory was divided into segments, each defined by a segment descriptor. These descriptors specify the rules such as whether memory could be read or written, whether it contained code or data, which privilege level could access it. If a program violated these rules, the CPU would raise an exception, forcing the operating system to handle the program. Now, the 8286 tracked these memory segments using two tables. The global descriptor table, which stored system-wide segments, and the local descriptor table, which stored process-specific segments. Together, these tables could theoretically address up to 1 gigabyte of virtual memory, a massive amount at the time. Protected mode also introduced a new interrupt structure called the interrupt descriptor table. Unlike real mode, which uses a simple interrupt vector table, the IDT provided structured, protected access to system-level interrupt handlers. This made the system more secure, stable, and robust. All of these ideas, multitasking, memory protection, privilege levels, virtual memory, and hardware-enforced security, form the foundation of modern operating systems. What began as a way to save excuse me, expensive CPU time on mainframes evolved into the sophisticated multitasking environments we use today. Every time you run multiple apps, switch tabs, or play music while browsing the web, you're benefiting from decades of innovation that began in the 1960s. And this is only the beginning of the story.